see with respect to the hyperbolic case, so previous case was it in a previous case is with respect to the steady flows. Previous case is with respect to the steady flows and unsteady invisible flow cases. So let us deal with a flow problem where it is having an unsteady invisible flows. Where it is having an unsteady invisible flow problems, right? So whenever we are saying it is an unsteady invisible flow problems, as we all know that the flow properties where are varying with respect to the flow properties are varying with respect to the time, where the flow properties are varying with respect to the time, right? So then it is called as an unsteady flows. Then it is called as an unsteady flows. If you are talking about the coordinate frame, so that is x, y, z, comma t. So that means here the flow properties are varying along with respect to the x, y, and z, and even with respect to the time variable. Even with respect to the time variable, that is dou rho by dou t, or dou v by dou t, or dou p by dou t. So that means where it is varying with respect to the time, even where it is varying with respect to the time. So then we'll call it as a unsteady fluid flow problems, unsteady fluid flows. And here we are dealing with the unsteady, and at the same time again the second case we are dealing with the invisible fluid flow cases. We are dealing with the unsteady and the invisible fluid flow cases. So that means is equal to 0. So where viscosity is not available, from our equation of the Newton's law, that is mu into du by dy, where it is defined along the only one axis. So where the Inviscid case states that the mu is going to 0. So when your mu is equal to going to 0, so that means the shear stress available on it is going to be 0. So that means there is this complete fluid flow, we are assuming it as an unsteady, and at the same time we are saying that it is in a Inviscid, unsteady and the Inviscid. So unsteady means where the flow properties are continuously varying with respect to the time, and when you are saying it is inviscid fluid flows, when you are stating it is an inviscid fluid flows, so there we are stating it that is viscous forces are not available in the fluid flow problem. So in this particular case, how do we approach with respect to the hyperbolic equations? How do we approach in respect to the hyperbolic equation? So if you see in the previous example, when we have drawn the characteristic curves, so the dx by dt, when you are referring to the previous sessions, so you can see, so this is the equation where it is stating dx by dt is equal to u minus c is one characteristic curve, and the another characteristic curve from the point B, or from the initial points, we got it as dx by dt is equal to u plus c. These are the two problems where it is being influenced, at the point P, So one, it is the left running characteristic curve, or other one is the right running characteristic curves. So they are being intersected at this point, and here if you see, that is dependent upon the points again E and D. That is dependent upon the point E and D. So so below this particular region is nothing but the domain of dependence, and above region is nothing but the region of influence, as we have discussed in the earlier sessions. Now as we see E minus C, the characteristic curve, where if you see, so that is dx by dt. So that means on the horizontal one we have x, so coordinate system, and the vertical one we have a t coordinate frame. So that is x comma t. So here I am discussing about the flow variables where it is varying with respect to the time. So that is the reason I have taken on the x curve, this tx. On the x it is taken on the distance, and on the y line I have taken it as the time. So where when I have drawn the characteristic lines of this one, so that is u minus c and u plus c, where u is the velocity of that particular characteristic curve or behavior of that particular characteristic curve. So when you are talking about this u plus c and u minus c, so here the yellow line and the blue line, when you have drawn it, and the intersection point, that is nothing but the point P, where it is influencing on that region. So that it is, so the below region of that particular point P, so that means where the initial conditions of this, initial conditions on this x, that is nothing but the distance from the E to P. So that is nothing but the distance from the E to D, if it is known to us, and accordingly the P will be dependent on that one. So that means P is being dependent on this particular distance, or P can influence on this particular distance. So which depends if your P is, if your D to E distance is being increased, then P will be influenced accordingly. So that means with respect to the P, I have to retake the region, how much I can expand on the x axis, how much I can influence, how much I am dependent on the x region is being focused. Now when I'm talking about this left running and the right running curves, right, so this is being influenced at this particular point P. So this is my right running curve, this is my left running curve. So on this particular point P, how they are being influenced, so that is nothing but are given by the characteristic curves of that equation, and when you're seeing, it's the representation of this one. So either you may represent with respect to the characteristic curves, or you may write it as, even in this one, so that is, you can write it as, you can write that it is A and B. You can write it as an A and B. So there are the two types of representation where I have went with the previous example. This is what, this is with respect to the previous example, or you can even discuss in this way. So that is where the points P is being influenced on this A and B. So that is the boundary data upon which the P depends. P depends on this one. And if you see the left running characteristics and the right running characteristics, this is a domain of, domain of dependence and region of influence. Domain of dependence and region of influence. Now you may ask a question, sir, what is the difference between the previous one to the current one when we are talking about the steady flows and the unsteady flows? Although it looks similar to the characteristic graphs or the curves we are drawing it in this one, how it is different from the steady flow? Have a look. Just have a look on screen. So when you are taking the characteristics, that is a method of characteristics, when you are plotting the lines here on screen, you can see have plotted it on x and y axis, have plotted it on x and y axis. Whereas in the current case, of the unsteady flows, whereas in that my coordinate system, that is x, y and z, I did not discuss with respect to the t. Whereas in the current one, it is being influenced by the time t. It is being influenced by the time t. So that means the time is effectively changing that one. So here you can say that it is at the time t instant, right? Here that t is equal to 0 instant, and here you can say that t is equal to t plus 1 instant or t plus t1 instant, right? So that time is initial time to the final time, so here I am talking with respect to the time, so that it is about the unsteady flows. Okay, if we just stay connected, no issue. I'll give you another example also when you're talking about the unsteady inviscid fluid flows, so no problem. You just see in this next one, I'm going to deal with the example, with examples also. I'm going to deal it before to that one. So when you're talking about the three-dimensional one, as it is influenced on the surface, as it is. So this is completely, I've taken it on the three-dimensional plane. So where on the z-axis my surface is being placed, and when I'm drawing this from the surface, when I'm drawing the left and the right on this one, so that is again similar to the previous approach, but here should be very careful about when you're drawing it in the three-dimensional curve. So that means all the variables when you're talking about, so that is whatever the vertical direction we are taking in that one, so that the direction of the fluid flow is dependent upon the time. Right? So that is about the domain of dependence and the region of influence when you're talking about the steady and the unsteady fluid flows. So here it is again point P, where we have shown it as the domain and the boundaries with respect to the three-dimensional flow field, where we are talking about the three-dimensional flow field solutions with respect to the hyperbolic equations. Okay. So let me go on to show you some examples, then you might be understanding it better, or you might be getting it in better understanding of this one. What will be along the z direction is whenever you are talking about any directional fluid flow, dependent variables also. So in the z comma t, x comma t, how your fluid flow variables are happening, so that would be addressed in this one. Now so the people will start asking the question, so where do we encounter this where do we encounter such type of flows? Oh, is it only the theoretical understanding? So here on screen you can see that where exactly are where we are supposed to model the equations related to the unsteady. And so this is the case where we can encounter the unsteady fluid flow problems, so where you can see with respect to the time, at every instant the flow properties are varying. So for example, if I have taken on the x and the coordinate frame, if I am taking it on the x and the t coordinate frame, I need to fix it on the body. As this particular fluid flow is varying with respect to the time. If you see at that instant of time t, this is what my aerofoil. So now right now my aerofoils have been paused. Aerofoil movement has been paused. Let me again show you one more moment when my time instant is. So this is at the fixed instant of time t. So let me remove this pause. Let me comment out pause. Then you just. So that means I'm not able to fix with respect to the time t. So when I'm talking about this time t, I'm not able to capture this particular coordinate frame of xy coordinate frame. As I can see on the screen, it is a two-dimensional frame. If I'm going within a steady flow problem, so then my solution may get at this instant. But when it is continuously, airfoil is getting plunging motion. When the airfoil is getting a continuous plunging motion, then my equation would fail in that case. So in that case, I need to address such type of problems within a Such type of problems I need to address with an unsteady fluid flow problems. So then only I can get this type of capture. Then only I can capture in the fluid flow. This effectiveness can be predicted. The best examples is airfoils in the plunging motion. On screen you can see how the fluid flows. How the fluid flows is continuously varying with respect to the time. So if you would like to see instant, let us stop this at an instant and see. Let us see at this time instant t. So for example, if this is at the time t1, this is x. Is at the time t is equal to t1. Now my time is constant. So now I have fixed my time. Right. Now I have fixed my time. So at this fixed time of t1, this is what I have got the capture. This is what I got the captured of it. Now if my time is continuously varying, just see. In this case, my t is not equal to t1. Every time my t is varying, in this case, my t is continuously varying. So I'm not sure what exactly equal to 0 to the limits t is equal to t1. So in between the 0 time to the t1 time, so it is making that wave motion in this particular fluid flow. So the fluid flow is making a wavy motion in this one. So that is what we are addressing in the x comma t. So at that instant where the fluid flow is, at this instant where the fluid flow. So this is the best example when we are talking about the unsteady fluid flows. Where do we encounter? So there we encounter the unsteady fluid flow problems. So this is an example. I hope this is clear to you now. So what exactly the hypersonic fluid flow problems are dealing with unsteady cases. The one such example where the time properties are varying with respect to the time. And here on screen you can see one more. So here in this one you can see how the fluid flow problems are done. It is shedding out, the vortex has been shedding out on this particular fluid flow. So these are all the cases where the influential point, initial points are effectively, so that means the domain of dependence has been, and the region of influence is complete domain, you can see by varying the velocity. So where the red and the blue colors are showing the particular along this particular axis, that is the x and t axis, x and t. So that means I am capturing the effectiveness of this particular fluid flow on the along with the time t. So let me check how the fluid flow is varying. So in order to capture this fluid flow pattern, see, you just see this is what the fluid flow pattern is happening. So here the vortex has been shaded like this, and the vortex has ended, and here the vortex is. And if you see second vortex, when the second vortex has been said, here the larger vortex has been generated, and here at this instant only this is a vortex, and this is the vortex shedding happened on this one, and it has formed a new, and it has completely formed a vortex on this one. So this is at the instant t is equal to t1. So at that instant of constant time only I am able to capture. Now the question comes, sir, how do we practically approach to this problem? So do we need to know how much time it takes for this particular initially in order to plunging motion or complete wave motion on this particular body? So in order to address this practically, so that means using any CFD tools, what we generally do is initially we'll solve the problem it as steady fluid flow initially. So very careful about this one. See, initially we'll address this problem as a steady fluid flow. Then later we'll introduce the time in that steady flows, and we will say that at this instant time t, this is steady flow. At this instant time t plus 1, this is again steady flow. At this instant t plus 1, it is again unsteady flow. So that means then we initially, what do we do as far as the computational approach is concerned? We will split it at the different times t1, t2, t3, t4, t5, t6, t7. Then we'll club up. Then we will club all the solutions of the steady flow, and we will vary with respect to the time. Then you will get the resultant variations like this. So that means while approaching to the computational one, we'll approach initially as steady, and later we will give the time derivative of it. And with respect to the time derivative, initially it will apply to the steady case, and later it will change it as an unsteady case. So that is how it approaches when you are approaching with respect to the computational fluid dynamics, how the fluid flow problem will be addressed in that. Okay, so let us just see how do we encounter the unsteady fluid flows in the unsteady fluid flows, and while with the plunging motion need to be addressed with there we encounter with an unsteady. Here are the examples how the flow would be released from an initial point to the final point, where with respect to the time variation. So here we have started with the initially t0. So that means same vortex shedding example I have brought it on screen. But how do we obtain the solution when we are doing it on paper? That's a theoretical approach how it is going to be resolved. So whatever we have seen, it is a graphical one, beautifully demonstrated on that. But when you are going for the practical one, this is what we are going to get it on paper. That means our understanding from that graphical base, to the real phenomena I have taken it on the slide number 43. I have taken it on the slide number 3. Right. So this states that how exactly we are going to address the problem and how it has to be reached to the people, how it has to reach to the people, or how it has to reach to the exact problem. Or for the better understanding or better visualization, what they will do is they'll apply it to the graphical user interfaces of this. So that may be using some tools, or they may be directly coding for the graphical user interface. So that is required when you're going for this particular computational fluid dynamics. When you're going for this particular computational fluid dynamics flow problems. Okay, so let us